In 2020, the United States didn't just start a trade war.
In particular with China, we're going to be doing a Section 301 trade action.
A large set of export controls.
We're taking in right now hundreds of billions of dollars. We're taking in billions of dollars of tariffs.
It cut China off from the most advanced semiconductor chips on Earth.
Cut China off from certain semiconductor chips made anywhere in the world with US equipment.
Overnight, China's access to the technology behind AI, weapons, and entire economies was gone.
The US government has announced new export controls designed to prevent China from accessing the most advanced AI chips.
This wasn't just pressure, it was a chokehold. And China saw it coming. For years, they had been building their own chip industry, trying to break free from foreign control. But there was only one thing they couldn't replace. Not the factories, not the engineers, a single machine. A machine so advanced, so precise, that only one company in the world can build it. And no matter how much money China had, they couldn't buy it. At the core of every modern chip is something extremely simple, a switch. It can only do two things, on or off. This switch is called a transistor, and when you combine billions of them together, they create something powerful enough to simulate logic, memory, even decision-making. But there was a problem. Early computers needed too many of these switches, and wiring them individually made machines large, slow, and unreliable. That changed in the late 1950s. Two engineers, Jack Kilby and Robert Noyce, discovered something revolutionary. Instead of building transistors one by one, they could place them all onto a single piece of material. They chose silicon, and that decision led to the first integrated circuit. From that moment, computers became smaller, faster, more powerful, and very quickly, this stopped being just a technological breakthrough. It became a strategic advantage. The United States saw the potential immediately, not just for economic growth, but for intelligence, defense, and military power. This is one of the earliest semiconductor chips from the 1960s. It had just 4 transistors. That was the limit. Because every transistor takes up space, and space on a chip is extremely limited, so if engineers wanted more computing power, they had only one option: make transistors smaller. Year after year, they pushed that boundary, shrinking each transistor, packing more into the same piece of silicon. By the late 1970s, that number had grown to nearly 70,000, and something unusual started to happen. The number of transistors wasn't just increasing, it was doubling again and again every couple of years. This pattern was first noticed by Gordon Moore, and later known as Moore's Law. And for decades, it held true. By 2010, a chip the size of a fingernail could contain over 1 billion transistors. Each one is just 32 nanometers wide. To put that into perspective, a human hair is about 80,000 nanometers thick. A blood cell is around 7,000. A bacterium, roughly 200. Now imagine something smaller than all of them, being built billions of times, perfectly, on a single surface. That's where the real problem begins, because at that scale, you can't build transistors the traditional way. You can't carve them, you can't assemble them by hand, you have to print them onto silicon using light. This technique is called photolithography, where beams of light are used to carve microscopic patterns into a chip. For years, the industry relied on deep ultraviolet lithography, using light with a wavelength of 193 nanometers. And it worked until it didn't. Because as transistors kept shrinking, the light itself became too large. You can't print something smaller than the tool you're using to create it. And suddenly, progress hit a wall. Modern chips, 7 nanometer, 5 nanometer, were now beyond the limits of existing technology, which meant one thing. If computing was going to continue advancing, someone had to invent a completely new way to build chips, a new kind of light, a new kind of machine. And in the entire world, only one company in the Netherlands managed to do it.
China quietly cracks a 5 nanometer without EUV.
The Chinese scientists have built a prototype machine capable of producing the world's most advanced semiconductor chips.
This is a modern chip. Inside it, there are over 100 billion transistors. Each one is just 5 nanometers wide. At this scale, manufacturing becomes extremely difficult. For years, engineers used deep ultraviolet or DUV lithography to build chips. That worked. up to a point. To go beyond it, engineers had to develop a completely new technology, extreme ultraviolet lithography, or EUV. EUV light has a wavelength of just 13.5 nanometers, about 15 times smaller than DUV light. This allows much finer patterns to be printed onto silicon. At a high level, the process sounds simple. First, generate EUV light. Second, shape that light using mirrors and a mask. Third, project the pattern onto a silicon wafer. But in reality, this is one of the most complex machines ever built. To generate EUV light, the machine fires microscopic droplets of molten tin, around 50,000 times per second. A low-power laser hits each droplet first, flattening it into a thin disk. Then a high-power CO2 laser strikes it again. This second hit is extremely powerful. The tin instantly turns into plasma, reaching temperatures hotter than the surface of the sun. When this plasma forms, it emits light at a very specific wavelength, 13.5 nanometers. That's EUV light, and this is the only reason the entire machine exists. Now, shaping this light is another challenge. You can't use normal lenses. EUV light gets absorbed by glass. It even gets absorbed by air. So instead, the system uses a series of ultra-precise mirrors. These mirrors are among the most perfect objects ever manufactured. Each one reflects about 70% of the light, and the light has to bounce across 6 to 8 mirrors before reaching the wafer, which means a lot of energy is lost along the way. That's why the original light source has to be so powerful. And all of this happens inside a vacuum chamber, because if air were present, the EUV light would disappear almost instantly. Now here's where it gets even more insane. These mirrors must be polished to near perfection. If you zoom into a normal household mirror, you'd see tiny bumps and imperfections. At the scale of EUV light, those bumps are massive obstacles. They would scatter the light in random directions. But EUV mirrors are different. If one of these mirrors were the size of Earth, its imperfections would be no bigger than a small card lying on the ground. That's how precise they are. Finally, the light reaches a photomask. Think of it like a stencil for the chip design. Some parts of the light are reflected, some parts are blocked. This creates a pattern. That patterned light is then projected onto a silicon wafer coated with a light-sensitive material called photoresist. Where the light hits, chemical changes occur. Those areas are then developed and etched away, forming the tiny structures of the chip. And this process isn't done just once. It's repeated over 50 times and a layer by layer to build a complete modern processor. So while the idea sounds simple, the execution is insanely complex. Even the smallest vibration can ruin the entire process. And that's why this is considered one of the most advanced machines ever built. This isn't just engineering, it's precision at the edge of physics. And there's only one company on Earth that has made it work: ASML. When the American government saw computers becoming more advanced and powerful each year, it built deep partnerships with chip companies to stay ahead in cutting-edge technology. But by the late 1960s, something changed. Chip companies realized they could make more money by selling to civilians as well. So they shifted strategy. The most advanced chips went to the government, while slightly less advanced versions were sold to the public. But there was a problem. Building chips was expensive, incredibly expensive. To cut costs, companies began moving manufacturing and assembly to countries like Japan, South Korea, and Taiwan, where labor was cheaper. Meanwhile, design and high-level engineering stayed in the United States, and the US government encouraged it. They pulled these countries into their orbit, made them partners, made them dependent, and in exchange, gave them economic growth. At the same time, the US restricted technology sharing with the Soviet Union and China during the Cold War. This gave the US military a clear technological advantage, but then something unexpected happened. By the late 1970s, Allied countries were no longer just manufacturing chips. They started designing their own. Companies like Samsung in South Korea and Toshiba in Japan began producing high-end chips independently. By the mid-1980s, Japan controlled over half the global memory chip market. And that made America uncomfortable. America pressured Japan heavily. Trade agreements were forced, tariffs were imposed, and Japan's chip industry slowly collapsed under that pressure. Taiwan was watching all of this, and Taiwan made a very different choice. Instead of competing with America, Taiwan decided to do one thing, just one: manufacturing. By the 1990s, a Taiwanese company called TSMC became so good at it that many US companies stopped manufacturing chips themselves and outsourced everything to TSMC. While the rest of the world pushed the limits of chip technology, China was rapidly growing economically, but lagging behind in semiconductor technology. During the Cold War, the US had restricted China's access to advanced chips. However, after the Cold War ended in the 1990s, relations improved and many export controls were lifted. China then attracted global companies to move their assembly operations there, offering lower costs. By the 2000s, China had become dominant in the global electronics assembly supply chain. Then China noticed a pattern. The chips were designed in America. The software to design them came from American companies. The machines that manufactured them were built in the Netherlands. But the machine itself requires certain components that are only manufactured in America, and the actual manufacturing happened in Taiwan and South Korea. China's role was mostly assembling the final product. That was it. The entire Chinese tech ecosystem relied on foreign countries, so China made a plan, build its own chip industry. No more dependency, no more foreign control. China began investing heavily, buying technology, and developing its own capabilities. However, due to limited access to advanced equipment, it could only produce older generation chips. Still, producing chips domestically helped China close the gap. But another problem remained. Many of the complex tools and equipment still had to be imported, leaving China dependent on foreign technology. To overcome this, China identified key choke points in the supply chain. They realized if they could build a machine like ASML's themselves, everything changes. So China quietly started recruiting ASML engineers. Later, ASML claimed that some engineers took sensitive internal documents to China. This triggered a strong response from the US government. In 2022, under President Joe Biden, the US imposed strict export controls, banning the sale of advanced chips to China. It also restricted Chinese companies from using US-based chip design software and pressured allied countries to follow similar rules. Despite these restrictions, China kept moving forward. It reverse-engineered older ASML machines using second-hand components and modified parts to build its own DUV systems. With this, China became capable of producing relatively advanced chips, but not the most cutting-edge ones, because those require EUV machines, which are far more advanced, and access to them has been effectively blocked by the US and its allies. Still, China is trying to break through that barrier, reverse engineering EUV systems, reusing older equipment, sourcing parts from secondary markets, and slowly building key components at home. According to a December 2025 Reuters report, China has made progress in EUV-related technology, but it is still not capable of producing chips with it. Some experts believe that by around 2028, China could potentially achieve full-scale advanced chip production using EUV. If that happens, it would reshape the global semiconductor industry and directly challenge decades of US dominance.